we continue our conference. Eiji Ogasa will talk about Seifert surfaces for virtual nodes and its relation with Floer homology. Eiji, please.
Yes, okay. Can I start?
Yes, please.
Oh, thank you very much. The title, thank you for, I'm glad to speak here. The title is Seifert surfaces for virtual nodes and Floer homology. This talk is based on my joint paper with András Juhász and Kauffman. Look at this one. Okay. Oh. Contents. Oh, please wait. Please wait. I put the PDF. Linking number in second surfaces. We cannot define linking numbers for lengths in a three manifold in general. However, we can do it for lengths in second surfaces. This is a second torus, and there is a link, two-component link in second surfaces. They are not null homologous, but we can define the linking number. Let JK be a two-component link in a second surface. J and K may not be null homologous. Linking number of J and K as follows. Take the projection of JK into F cross minus 1. Assume that the projection map is a self-transverse immersion, just as we can take a diagram of a classical link in the plane. We can use such diagrams, which is the projection in the surface F cross minus 1. We give each crossing point of J and K a sign +1 or -1. By using the orientation of J, that of K, and that of F cross minus 1, the linking number is half of the sum of the signs at all crossing points. Note, the linking number of two circles embedded in the second surface take a value in not only integers, but also half integers. And further, if F is the two sphere, this is the linking number of classical links. This is an example. I put the PDF of this one. I put this PDF file in the chat line. Look at it. Seifert matrices for null homologous nodes. Let M be a closed-oriented three manifold. There may be a non-zero cycle. There may be a non-zero cycle node K in M. In general, we cannot define a Seifert surface, Seifert matrix, or Alexander polynomial. In the second surface case, although there are non-zero cycle one nodes, but we introduced a few kinds of Seifert surface, Seifert matrix, and Alexander polynomial for all nodes in second surfaces. Even if nodes are non-zero cycle one node, we can define Seifert surface and Seifert matrix. This is one of our one of our results. We discuss only null homologous nodes in second surface before we discuss both null homologous nodes and non-zero cycle nodes. we discuss all knots in thickened surfaces, but first, let's discuss null homologous case. A knot K in a thickened surface is null homologous if and only if K bounds the Seifert surface. However, we encounter the following problem. This is a torus, net of the torus, and the thickened consider thickened torus. And this is trivial knot, and Seifert one of Seifert surface. Let L be a link in a thickened surface U and V. Seifert surfaces for L. In general, the Alexander polynomial defined by U is not balanced to that defined by V. Let U be a disk in a T2 cross 0. Let L equal du. That is, L is the trivial knot. Let V equal T2 cross 0 minus interior U. U and V are Seifert surfaces for L. A Seifert matrix defined by U is the empty matrix. This is a trivial knot in torus. So there is a Seifert surface and there is a Seifert surface. In this case, a Seifert matrix X defined by V is 0, this one, and elements are half integers in general. We encounter a new kind of Seifert matrices. The Alexander polynomial associated with U and V is the balance class of 1 and 1/4 cross T plus 1 square, respectively. Disk, U is disk, then 1. V is not a disk as that one, then it's not 1. Note the elements of Seifert matrices are not only integers, but also half integers. This is a very new feature, I think. Let's investigate this one. We introduce new Seifert surfaces. We call it twin Seifert surfaces. L be a two-component one link in a thickened surface. L is null homologous. There is a two chain such that the boundary is L. The differential here, differential is the differential acting on chains. Anyway, this is suppose it's chain. We do not move L by anisotropy for now. Let P be any point in F. P cross minus 1, 1, and O, forget. Bar epsilon intersect transversely. Sorry, bar sigma, okay, anyway, Greek letter. Assume that P cross the interval and have 0 algebraic intersection numbers, then we call this two chain a type 0 two chain for L. Let K be an oriented knot in a thickened surface. K may be not null homologous in F. In thickened surface, in general, a knot is non-zero one cycle. But we consider a kind of Seifert surface. We introduce a kind of Seifert surface. K in F cross I. Take a copy. K at, I will define it soon. K at in F hat F and F hat, F roof is a copy. Reverse the orientation of K and consider minus K or minus K star. K at is minus K or minus K star. Put it here. They are symmetric with respect to F cross zero. Sorry, F. Anyway, F. It is F. Imagine this figure. F cross I and K in F cross I and take minus K or minus K star. The K at stand for either minus K or minus K star. K and K at is a vanishing Wien cycle by the definition. There is a Seifert surface W for K and K at. This is an idea, our idea. This is a crucial idea. Take K, K at, F, F roof, W as above. If W is a type 02 chain for K and K at, we call W a twin Seifert surface associated with K and K at. We don't move K or K at by an isotopy now. Seifert surfaces are connected by the definition, and the twin Seifert surfaces are connected too. We take K and minus K or minus K star. The disjoint unions are null homologous. And there are many kinds of Seifert surfaces, but we take zero chain, zero type. K may be not null homologous, but there is a twin Seifert surface. Then the GS equivalence class of Seifert matrices associated with twin Seifert surface is a not type invariant. We move K by an isotopy, then we move K at together. So we define Seifert surface, twin Seifert surface, new Seifert surface, and define Seifert matrix, new Seifert matrix, and define define a new Seifert matrix. For twin Seifert surface, Seifert matrices are invariant. By using Seifert matrix, twin Seifert matrix, we define the these twin polynomial as in classical case. These twin Alexander polynomial we defined. The further, the Seifert matrix, twin Seifert matrix have signature. Call it the twin signature. And twin Alexander polynomial and twin signature are defined for both K and minus K and minus K star. So the idea is we put minus K or minus K star, then we can define Seifert surface. And we can define Seifert matrix, and we got a twin Alexander polynomial and twin signature. It is a natural generalization of a classical case. That these twin Alexander polynomial and the twin signature are topological invariants of nodes in secant surfaces. If k at equal minus k, there is k with twin signature not zero, is not equal zero. The twin signature is a non-trivial invariant. And further, zeroth twin Alexander polynomial is zero if k is classical. If it is not zero, it's non-classical. In S3 case, in the class, if f is S3, in classical case, twin Alexander polynomial is square of Alexander polynomial of J or J at. Okay, Alexander polynomial of J and J at is a square. And if k is classical, all coefficients of Alexander polynomial are integers. The root, non-zero root is multiplicity is n, is greater than 1. And further, a minus and a minus star equal. And they are virtual equivalent. The handle stabilization of virtual theory doesn't change twin Alexander polynomial and twin signature. So twin Alexander polynomial, twin Alexander polynomial for virtual nodes or links in secant surfaces have a different property in the case of classical case. Minus and minus star are different. Multiplicity is not 2. It means twin Alexander polynomial are invariant, mirror sensitive, and further mirror sensitive and can obstruction of being classical. The twin Alexander polynomial twin signature distinguish some virtual nodes from their mirror images and can obstruct a knot from being classical. This is an example. We show explicit examples. It's a net of torus. And calculate Seifert matrices and twin Alexander polynomial. And there are half integer. Elements are half integer or integer. We show another example. This case, twin signature distinguish mirror image. Virtual case. And K is non-classical and the twin signature distinguish mirror image and original. Oh, I submitted the question. And next, Floer homology for nodes in secant surfaces. K in secant surface. Make F cross S1 from secant surface. Put K and K at and make F cross S1. There F cross S1 is cross-oriented three manifold, and K in cross-oriented manifold. Even if K is not null homologous, you have defined Suchard-Floer homology. We can apply it. Or surgery at K or K and K at R framing surgery, we get the three manifold. We can define Higard-Floer homology by Osbach-Zabo. Anyway, we can define Floer. Anyway, we defined Floer homology for length in thickened surfaces. And we apply this for virtual lengths. Anyway, we introduce an invariant epsilon k for any virtual knot k via Floer homology for lengths in thickened surfaces. If this is 0, then k is the trivial knot. We use Osbach-Zabo's theorem about genus. Anyway, we use Floer homology and can investigate k is trivial or not. Anyway, we use Juhász-Floer homology, Osbach-Zabo Floer homology. And we use the balance Gola delta invariant via Floer homology. Can obstruct virtual knot being from the trivial knot. Anyway, surgery on three manifolds and consider four manifolds which bound three manifolds and apply their result. Oh, and there are many kinds of Alexander polynomials discovered before our result. The definitions are very different. It is the first time to use Seifert matrices. Seifert surface and Seifert matrices and signature are probably the first example that we did. And their definitions are very different. What kind of relations there are? What kind of relations are there? Oh, chat question. Eiji, you have 2-3 minutes left. I know, just less than 1 minute now. Yes, I finished my talk. Thank you very much. I put the PDF again. Please take it.
Any question? Okay. If there's no question, let's take the speaker again. Thank you very much.